So right now it's just my mic here that is unmuted. Yeah, okay. Yeah, so I'm going to try again. So, Shervin, can you hear me?
Yes, I can hear you very well. Didn't hear you very well, Stefan. Probably need a microphone or.
Shervin, were you informed of the proceedings to elect the president of the jury?
Yeah.
Okay, thank you.
The jury members are the reviewers. Right, Reverend Bagari, hosted the director is Miguel and Kinetic. So Alejandro. Right?
Yes.
Was the research?
Okay. Thank you for the introduction, and thank you everyone for being here. Today I will be presenting the work that I've done in my PhD thesis under the supervision of Tarner Sayadi, Miguel Fosas de Panda, and Vincent Chinadec on simulation and optimization of interfacial flows. So interfacial flows, by interfacial flows we refer to flows where a sharp interface separates two immiscible faces. They are present in a wide range of nature and industrial applications in processes such as evaporation, cavitation, and atomization. And here I present you a few examples. So we have a falling stream of water that has broken up due to a plateau Rayleigh instability. We have some rain droplets over a leaf, and we have some spray generation in an injector. As in many other types of flows, optimization is very important for many applications. And for example, in the case of electrolysis, we want to reduce the bubble formation. And in the case of inkjet printing, for example, we want to optimize the size of the droplets. So my thesis is divided in two different parts. First part, where I developed a flow solver for numerical simulation of interfacial flows. And a second part where we assess the performance and proposed improvements to optimization methods that are well suited for this kind of flows. So now I will be presenting the first part of the presentation where I will talk about the numerical solver that we developed. So we consider the specific case of free surface flows with contact line dynamics. Free surface flows are interfacial flows where the surface is subject to zero normal and shear stresses, and we consider the case where the effect of one of these phases can be simplified. Now, contact line appears at the triple intersection between the solid wall and the free surface, and numerically there's a contradiction between the no-slip condition, boundary condition that we impose at the wall, and the motion of the interface, and we have to use some model in order to solve this. Here I present you a sketch of the flow configuration that we'll be analyzing. And as you can see, there are many different boundary conditions involved. We have at the wall the no-slip boundary condition. We have the stress balance equation at the free surface. And at the contact line, we decided to use the Navier-Slip boundary condition. So there are different problems and choices we have to do in order to simulate this kind of flows. First, the presence of the moving boundary adds an extra layer of complexity compared to simulations of stationary bodies, because now we have to track this interface. In terms of grid configuration, we have different possibilities, and that affect the way we impose the boundary conditions. And all of these affect the conservation properties of our numerical solvers. So, in terms of interface representation, we could use front tracking methods, where the interface is defined by a set of connected marker points, They are very accurate, but are very hard to implement. Then we could use front capturing methods, where we have a scalar field that defines our interface, and that is commonly used called the marker function. So we have diffuse interface methods, such as the phase field, where the interface spans a few cells, and the sharp interface methods, such as the volume of fluid, where the marker function represents the volume fraction of one of the phases, or the level set method, where the marker function represents Euclidean distance from each point to the interface. In terms of grid configurations, we could use body conforming grids, that's the one that we have here at the top, where we have a great flexibility in terms of cell size, but they can be very complicated to generate. And in the case of interfacial flows, due to the moving boundary, this means that we will have to regenerate a new grid at each iteration, which in terms of overall cost can be very, very expensive. So the alternative is the use of non-conforming grids, which are very simple to generate, and but they come at the cost of having that the imposition of the boundary conditions is more complicated compared to body conforming grids. So we find two different types of methods to impose the boundary conditions on non-conforming grids. We have diffuse interface methods, such as the immerse boundary by Peskin, where the boundary conditions are imposed by adding extra terms in the momentum equations via Dirac delta functions, but they do not allow strict conservation of physical quantities. Then, on the other hand, we have sharp interface methods, such as the cat cell or the ghost cell, where the boundary conditions are imposed by modifying the discrete operators, and for example, in the case of the cat cell, by using geometric information. And the good thing about these methods is that they can potentially conserve physical quantities such as kinetic energy or momentum. The problem, for example, for the cat cell is that there are too many different cell configurations that we have to handle individually, which makes very difficult to impose the boundary conditions. In the literature, we can find some examples of conservative cat cell methods, but there's not a single cat cell method that is fully three-dimensional, and none of them are used for fluid-fluid interfaces. They're always used for fluid-solid interfaces. So for interfacial flows, the diffuse interface method leads to what is called the one-fluid formulation, where we have a single set of equations for all the phases, and where the effect of the surface tension is accounted for by an extra term in the momentum equation. But the problem is that when we have phases with very different properties, such as density, then the linear systems of equations that we have to solve may be ill-posed. For sharp interface methods, they lead to the two-fluid formulation, where we have separated sets of equations for each phase, but the imposition of the boundary of the jump conditions at the free surface can be very complicated. And as I said before, cat cell methods can potentially conserve kinetic energy, for example, but they do need to satisfy a number of requirements in order to do so. So in the context of the incompressible Navier-Stokes equations, we could use collocated grids, which are simple because we have a single set of control volumes for all the fluid variables. But for compact stencils, we know that they do not satisfy the divergence-free condition. And for non-compact stencils, we have oscillations in pressure and velocity due to the decoupling of both. So the alternative is the use of staggered grids, which are more complicated because now we have different control volumes for different variables, as the sketch that we have here, where you can see that the velocity components are not collocated with pressure, but they do satisfy the divergence-free condition, and they don't present oscillations in pressure and velocity. Now, in order to conserve kinetic energy in the inviscid limit, we need our discrete operators to mimic the properties of the differential operators in the Navier-Stokes equations. Namely, we need the divergence to be minus the transpose of the gradient, we need the convective term to be skew symmetric, and we need the viscous operator to be symmetric positive definite. So as a summary, in our numerical solver, we decided to use the level set method, mostly due to its simplicity in the implementation, so we could focus on other parts of the solver. We decided to use non-conforming grids, so the mesh generation procedure is not expensive. We impose the boundary conditions using the cat cell method. And finally, we use a staggered grid arrangement in order to conserve the different physical quantities that I mentioned before. So, as I said, in the literature, we don't have a fully conservative, fully three-dimensional cat cell method. And in this first part of my work, we have taken steps into this direction. My work is based on two different PhD theses, one by Yonji Bei, where he developed a Katzel method that I have modified in my PhD, and then the thesis of Tomás Fulana, where he developed an in-house code written in Julia to solve the Stefan problem, and where he implemented the Katzel method of Yonji Bei, and that where I have implemented all my developments. So now I will be presenting the numerical method that we have developed. The Katzel method, it's a finite volume method based on the application of the divergence theorem. If we consider this case here at the right, where we have a computational cell intersected by an interface gamma, which divides the cell in a gray and white phases, and if we apply the divergence theorem to a constant vector field defined on the white face and this constant vector is only defined in one of the Cartesian directions, then we arrive to what is called the geometric conservation law that basically relates the cell faces, here in red, AX and AY, with a linear representation of our interface gamma tilde, here in green. So now, if we want to obtain the divergence of a certain vector field defined at the cell faces and at the interface, we arrive by applying the divergence theorem to this expression here in the middle, where if we substitute the geometric conservation law, we arrive to this other expression here, which is just function of the volume moment V and the surface moments AX and AY. This means that our discrete divergence doesn't require any explicit information about the interface. Now, as I said before, we have a staggered grid arrangement. This means not only that the field variables are not collocated, but also that the control volume where the gradient is defined is not the same that the control volume where the divergence is defined. Therefore, we defined a new set of staggered grids, one in X, I'm showing here with dashed lines, and one in Y. And we define this staggered grid by tracing vertical and horizontal lines passing through each cell centroid, here with a cross. And these lines define a new set of geometric moments. So first, surface moments, here in green, Bx and By in the y direction. And this additional set of surface moments define an additional set of volume moments, here Wx in the x direction and Wy. Now, if we apply the divergence theorem to this control volume here at the right, in order to obtain the gradient of a scalar field, we obtain this expression after substituting again the geometric conservation law, which again is only function of the volume moment Wx and the surface moments Bx. So again, we don't have any explicit information about the interface. In order to compute these geometric moments, all the information that we need from our interface are the intersection points of the interface with the cell faces, which are these black dots here in this picture. And as I said, we use the level set method to define the interface. The level set is a signed distance scalar field where the interface is defined by the zero ISO level. This means that on one side of the interface, we have positive values of the level set, defining one of the faces. And on the other side of the interface, we have negative values of the level set, defining the other face. Apart from these intersection points, from the level set, we will have to compute also the normal unit vector and the curvature that we will use to impose the boundary conditions at the free surface. So once we have the expressions for our discrete gradient and divergence, we can put them in matrix form. And the key idea here is that we have one matrix that computes the contribution from the bulk field, here for the gradient multiplying p omega, and here for the divergence multiplying q omega. And we have another matrix that computes the contribution from the boundary field, here multiplying p gamma, and here multiplying q gamma. I'm not showing today the exact definition of these operators, or they have extra slides with their definition, but they are very simple to set up. They are just defined as the multiplication of elementary matrices that are either diagonal or bidiagonal, and that store the information of these geometric moments and of the structure of the final operators. So once we have defined our Katzel operators, we can use them to discretize different systems of equations. And first, we consider the Poisson equation, which you have here in the first line, subject to a generalized Robin boundary condition here in the second line, where we have these scalar coefficients, A and B, that we can use to set different types of boundary conditions, like Dirichlet, Neumann, or Robin. So we use our operators to discretize the system of equations, and we arrive to this system here, where the first row corresponds to the Poisson equation itself, and the second row corresponds to the boundary condition. And this is one of the main points of our methodology, and the main difference with other methods that we can find in the literature is that we also discretize and solve for the boundary condition. And this has some consequences. First, for us, it's very simple to mix different types of boundary conditions because these scalar coefficients, A and B, are transformed into these diagonal matrices, YB and YA, where each element in the main diagonal can be used to set a different boundary condition at different locations of the domain. Then you can see here that in the solution vector, we have two different components, P omega and P gamma, where P omega is the vector for the bulk field and P gamma for the boundary field. This means that as part of the solution to our problem, we obtain the values at the boundary field. And this removes one source of error because now we don't need to interpolate or extrapolate the values at the interface from the bulk field, which is very convenient for many applications in interfacial flows which require the use of values at the boundary. But of course, all of this comes at the cost of having to solve a larger system of equations. Now, we can use the Katzel operators to discretize the incompressible Navier-Stokes equations. I'm not showing today the definitions of the convective term and the viscous operator, but they are also defined based on elementary matrices, diagonal or bidiagonal, and that are very simple to set up. So, incompressible Navier-Stokes equations result in a saddle point system of equations because the pressure doesn't show up in the divergence-free equation. And the most common method that we use to solve this type of equations are projection methods. So we decided to use the pressure projection by Brown and co-authors, which is a very common choice for these equations. And now we can apply our method to solve some flows. So first, we consider the case of a flow around a cylinder at Reynolds 100, which is a very typical test case for validation. We tested 4 different grids with the same domain size and different levels of cell refinement. And here at the right, I'm showing you the streamwise and vertical components of the velocity for the finest grid, G4. We performed a convergence analysis using the average drag coefficient, and we obtained a convergence order of 1.6, which is acceptable since our Katzel method is at most order 2. Now here at the right, I'm showing you a comparison between the Strual number, the root mean squared lift coefficient, and the drag coefficient comparing with other numerical simulations and with experiments, where we can see that we have a good agreement in all of these parameters. Okay. So far, we have only considered stationary interfaces, but we are interested in free surface flows. So we have to consider the case of moving interfaces. And now I'm going to explain how we do this. So for the level set, it's very simple to move the interface because we just have to solve this advection equation, which we discretize using the stabilized inflow implicit outflow explicit scheme by Mikula and co-authors. The problem with the advection of the level set is that when we advect it, it may lose its distance property. And I give you this example here where first the level set is defined in a cylinder, and you can see in red the different iso levels that are equally spaced, meaning that they have the distance property. And then we advect the level set just around the interface, and we arrive to this level set here at the right, where you can see that far from the interface, the iso levels are still equally spaced, meaning they have the distance property, but around the interface, they have changed its spacing, meaning they don't satisfy the distance property. So this means that at the next iteration, when we try again to advect the level set, the advection equation is not going to work as we are expecting. And what we have to do is we have to recover the distance property for the level set by enforcing the level set to satisfy the iconal equation here. There are different methods that we can use to do so, but we decided to use methods based on the solution of the Hamilton-Jacobi equation in pseudo-time. We performed a validation comparing different schemes because the solution of this equation it's not very simple because we need to modify the level set in the whole domain, but we cannot modify the zero iso level defining the interface. So there are different methods that we can use to avoid this. After some validation, we decided to use a Win of 5 scheme for the spatial derivatives. the subcell fix of Russo and Smerica for around the interface, so it doesn't move, and a total variation diminishing second-order Runge-Kutta method for the temporal integration in pseudo-time. So now, once we can move our interface, we can apply it to our method to free surface flows. So the first test case that we consider is a sessile drop on a straight surface that we initialize at a 90-degree contact angle here in the middle. We impose a different contact angle and we let the drop move. So here at the right, you have a comparison between simulations and the theoretical solution for the ratio of final and initial radius of the drop. So in this case, we don't have any gravity, and therefore the shape of the drop is a perfect sphere or cylinder. So here you can see that the comparison we have a good agreement with the theoretical solution. Now I'm showing you the evolution of the mass of the drop for different contact angles, and we can see that for contact angles smaller than 90 degrees, we always have a mass gain, and for contact angles larger than 90 degrees, we always have mass loss. And as I said, the Katzel method that we are developing is conservative, but the problem is that level set method is not. And so we verified which was the main source for this mass loss gain, and we checked that it was due to the imposition of the boundary conditions to the level set to impose the different contact angles, and we verified that we had a first-order convergence as we would expect if this was the case. So before we considered a straight surface, but we want to apply the contact line dynamics to arbitrarily oriented solid walls. So we need now two interfaces intersecting our cell. To do so, we use a second level set to define the second interface. And now the problem is that the surface moments that we use to compute to build our operators, they cannot be computed just from the intersection of each of these interfaces with the cell faces, which are these black dots here. Why? Because if we consider this case, where the blue shaded area is the liquid phase where we are solving our equations, then if we consider these points to compute our surface moments, the length of the interface that we will considering will include both the solid and dashed part of the lines. Therefore, what we have to do is, apart from those points, consider also the point where both interfaces are crossing. And this way, we only have the contribution, or the length that we will consider just includes the solid part and not the dashed part. The other consequence is that now we have two interfaces with two corresponding boundary conditions and with two corresponding boundary fields. So we have to add in our definitions of the discrete gradient and divergence an additional term here and here in red with the contribution from this second interface. So as a summary, we will have to define three different sets of surface moments. One here at the left that will be used to build the Katzel operators that compute the contribution from the bulk field, and two different sets of surface moments that will be used to build the Katzel operators that are used to compute the contribution from the two different boundary or interfaces in red and in green. So once we have modified our methodology to have arbitrarily oriented walls, we can apply the method to we have considered this test case where we apply the method to the sessile drop over a cylinder that again we initialize at a 90-degree contact angle. Here we impose again a different contact angle and we let the drop move. And here we compare the theoretical solution and our simulations with other two references, again for the ratio of final and initial radius, and we can see that we have a good agreement. And these two references use the Katzel method to impose the boundary condition at the solid wall, but they use the one fluid formulation at the free surface instead of using also the Katzel method to apply this boundary condition. And as a final test case, we consider a falling droplet subject to gravity that is initialized underneath a rough wall with an initial radius of 0.5. We set the Reynolds number to 1 and the bond number to 10, and we will see that due to the gravity, the droplet will start to fall. At some point, it will break up, and we have placed at the bottom another solid wall where that it will be hidden by one of the drops. So I'm gonna close the case. Okay. And here, one of the things that we can see with respect to the other cases, that due to the presence of the gravity, now the shape of the wall of the droplet that hits the bottom is not perfectly spherical, and also because the droplet at the top has a bond number much smaller. Now surface tension is large enough to keep it in contact with the wall. So okay, so now I'm going to present the second part of my work, where we have considered the optimization methods that are well suited for the optimization of interfacial flows. So, optimization methods are usually divided into gradient-based and derivative-free methods. Gradient-based methods work by iteratively taking steps in the direction of the local gradient. And derivative-free methods do not use the gradient, and they rely on some kind of stochasticity to converge towards the minimum. So, gradient-based methods can be divided on first order if they just use the gradient, and second order if they also use the Hessian or an approximation of the Hessian. And the main question here is how to compute the gradient. So we could use analytical expressions if we had the exact definition of our objective function, which is not the case in fluid mechanics. We could use finite differences, which require one function evaluation per dimension of our problem, and therefore for very high dimensional problems, they are not they don't work so well because they are very expensive. Then in fluid mechanics, the adjoint method has been widely applied since it's the first applications by Pironneau in fluid mechanics and Jamieson in aerodynamics. The problem is that it requires the implementation of an adjoint solver, which in the case of interfacial flows can be very, very complicated, if not even impossible. As an alternative, we have methods that use approximated gradients, such as the stochastic gradient descent. So these methods provide a very fast convergence rate, but the problem is that when we have very complex objective functions with many local minima, they get stuck in these local minima, and they do not allow convergence towards the global minimum. As an alternative, we have derivative-free methods, which, as I said before, do not require the evaluation of the gradient. Sometimes they are referred to as black box methods, because the only information that we have about this, about the objective function is the result that we get when we evaluate it. There are many different alternative methods, such as coordinate descent, pattern search, particle swarm optimization, or evolutionary algorithms, among many. And the good thing about this method is they can ensure convergence towards the global minimum, but they require many function evaluations. And in the first at the beginning of my thesis, we consider an optimization method based on the coordinate descent combined with the use of surrogate models that led to this publication here. And what we found is that when we have very complex functions, they work well and they outperform the gradient-based methods. But when we have simpler functions, which are also present in many applications, then we cannot beat the performance of gradient-based methods. So we try to find a method that had the convergence rate of gradient-based methods, but didn't require the use of an adjoint solver. And therefore, we decided to test the performance of ensemble variational method, or EnVar. So, ensemble variational methods were originally developed for data assimilation problems by Liu and co-authors, and have been applied widely in this field. I have here some references. It's a hybrid approach between variational methods, which are basically adjoint methods, and ensemble filtering, where they use Kalman filters. And in essence, it's very similar to stochastic gradient descent methods, in the sense that they use approximated gradients. Unfortunately, there are not many examples of application of this optimization method outside data assimilation problems. So how does this work? Well, as in any other gradient-based method, we converge iteratively towards the minimum. So at each iteration, we have a point that we call here the center, here in red. And around this point, we are going to define a set of ensemble members, which are perturbations around this center. So here, in this case, we consider just one, which is this black dot here. And the idea is that the approximated gradient in where we're going to move is going to be defined as a linear combination of the directions defined by this set of ensemble members. So in this case, we just have one ensemble, meaning that we can move only in the direction defined by it, which is this blue dashed line. So now we are going to see more in details how it works. We have a function that we call observation function in H, which we apply to our set of design parameters, x, and that returns a vector, y. Then our actual objective function is the function f, which in the context of EnVar optimization, it's usually defined as a quadratic function to exploit the benefits of this method. And the idea is that we are going to define an augmented cost function where the first term is the actual objective function that we are optimizing, and the second term is a penalization where that is enforcing the method to not take huge steps between two different iterations. So, as in any other gradient-based method, the next point is based on the previous point minus the step size, multiplicating the gradient. And the key question is how do we compute this step size and, in our case, also the gradient. To do so, we define the perturbation matrix, P, which is defined by the ensemble members and the center. The ensemble members are computed using a normal distribution centered around the center xi and with standard deviation sigma p. And each column of this matrix P is defining one of the interfaces where we can move in our gradient. Now, the most computationally expensive step of this method is the obtention of the observation matrix H, where we just apply the observation function H to each of these ensembles and centers to obtain this matrix here. So, in the EnVar method, we replace the gradient and the step by the multiplication of the perturbation matrix P by a vector of weights W, where each element on this vector is going to weight the relative importance of each of these directions defined in the perturbation matrix. So we replace this in the update step and we obtain this expression. And then if these ensemble members are small perturbations around the center, this linear approximation here holds. And we can replace it in our cost function to obtain this expression here, where we have the augmented cost function as function of the vector of weights W. So the only remaining step is computing this vector of weights. To do so, since we have a quadratic function, we can use the Newton method by first deriving to obtain the gradient and then to obtain the Hessian. And we have this, at the end, this system of equations here at the bottom right, that we can use to compute the weights. So something that we thought was missing in the literature from people using this method is parametric analysis of how the different parameters affect the performance of the method. And we decided to analyze the influence of the dimensionality of the problem, the number of ensemble members, and the parameters sigma h and sigma p, where sigma h is used to weight the relative importance of the penalization term in the objective function, and sigma p gives you its standard deviation to compute the ensemble members, so how far are these ensemble members from the center. And in order to measure the performance of the method, we use the geometric mean for a given combination of the parameters, averaged over hundreds of optimizations. So I will be showing plots like this one here at the right, where for a given combination of dimensions and ensemble members, I show you how the parameters sigma h and sigma p modify the performance of the algorithm. And here we can identify three different regions. First, at the top left, we have a region in yellow where the algorithm is not working very well. And here what is happening is that sigma h is large, meaning that the penalization term is too important, and therefore we are just optimizing the penalization term. We are not optimizing our objective function. Then here at the right, we have a region in green where sigma p is too large, meaning that the ensemble members are too far away from the center, and therefore the linear approximation doesn't hold anymore. And then finally, we have a region where the algorithm is performing well, here in blue, and we will have this kind of regions in all the combinations of parameters that we will be seeing. So we used two different test functions. First, the Rosenbrock function, which is almost a quadratic function, and meaning that the approximation that we do for the Hessian is almost exact. Therefore, the method should work very well. And then we have the modified Bill function here at the bottom, which is not so quadratic. Therefore, the Hessian is not going to be so good. The approximation of the Hessian is not going to be so good, and therefore it's a better method to analyze the performance of the algorithm for more general applications. So here I'm showing you for the Rosenbrock function, we have at the left 5 dimensions and 1 ensemble, 5 dimensions and 5 ensembles. And then at the right, for the Bill function, we have 4 dimensions and 1 ensemble, and 4 dimensions at the bottom and 3 ensembles. And what we can see is that for a low number of ensemble members, the size of the region with a good performance of the algorithm is large. And as we increase the number of ensembles, at some point we have a transition to a point where the size of this region is very narrow. And what we can see, interestingly, is that this happens for all the number of dimensions, for all the functions, but the point at which the algorithm transitions from having a large region to a small region, it happens at different points depending on the type of function that we were using. So for the Rosenbrock, it always happens when the number of ensembles is exactly the same than the number of dimensions. But for the Bill function, this happens sooner, meaning that when the function is close to a quadratic function, the transition happens later, and when we have a less quadratic function, the transitions happen sooner. So here I'm showing you for the Rosenbrock function the evolution of the geometric mean as function of the iterations for 5, 10, and 20 dimensions. And in blue, we have considered the same combination of parameters sigma h and sigma p inside this region of good performance. And what you can see is that starting from the solid line with just 1 ensemble in all the cases, as we increase the number of ensembles, we improve the performance of the method until we reach the case where the ensembles are equal to the number of dimensions, where we get a plateau in the performance. And then in orange, I showed you a point inside this good region with a different combination of sigma h and sigma p, where for the same number of ensembles, we again can improve the performance of the algorithm. So in order to improve the performance and to increase the robustness, we propose 2 different improvements. So first, the use of a variable sigma h coefficient, so that the relative importance of the penalization term stays constant during the whole optimization procedure. And then, as I said before, this method is very similar to stochastic gradient descent, where the use of momentum is widely applied. And the idea is that we use the previous update of the control vector for the next point, so which will be this first term here in red with this decay coefficient beta. And now for Nesterov momentum, we also evaluate the gradient at the future point, so we add this last term here in red. And then the linear approximation becomes this last expression here at the bottom. So we verified the performance of the algorithm with these improvements, and what we saw is that for both functions and for all the number of dimensions, first, the size of the region with good performance has increased a lot in all the cases, and also for many of the cases, we are able to get to a better minimum than what we had before without the improvements. So, as I said before, we have an approximation of the Hessian, so now we wanted to verify how close we were to a second-order gradient-based method. And here, for the Rosenbrock function and the Bill function, and as many ensembles as dimensions, we compare our method in terms of wall time and CPU time with the LBFGS algorithm, which is a quasi-Newton second-order gradient-based method that uses approximations of the Hessian based on the gradient. And what we see is that for the Rosenbrock function, the performance is almost the same for all the number of dimensions, and we get, in all the cases, to the global minimum. And for the Bill function, we can see that at the beginning, the performance of the LBFGS method is better, because now the approximation of the Hessian is not so good. But interestingly, the LBFGS gets stuck in a region where the gradient is not very steep, so it takes a lot of iterations to improve. And since the EnVar method has some stochasticity, then we're able to skip this region and converge towards the global minimum. And finally, I will show application of the EnVar method to the optimization of interfacial flows. So we consider this case that I showed you before with a falling droplet, where the objective function was set to the volume of the drop that falls after the breakup. We parameterize the rough wall with 8 design parameters that we aim to optimize. And here for the initial guess, which is this case, we obtain an initial volume of 19% of the total volume. And then we apply the EnVar method. And we see here at the left the convergence rate of the optimization method, where we arrive to a plateau, meaning that we arrive to the global minimum. And we can see that we have reduced the volume of the drop to 60%. And interestingly, we don't have a symmetric wall. And what is happening, as I would expect at least, so what is happening is that we have a current that is being generated at the free surface that is triggering the breakup sooner than before. We have less volume of the drop below the breakup point, and therefore we have reduced the size of the drop. And now I would like to conclude. Regarding the first part, we have implemented a Katzel method where we can easily mix different types of boundary conditions. We have direct access to the values at the boundary, meaning we don't have to do any interpolation to obtain these values. We have applied it first to canonical cases around stationary bodies. And then we extended the Katzel method to handle complex moving geometries in the context of free surface flows and contact line dynamics. We applied it again to canonical cases with good agreement between our method and methods that use the one-fluid formulation at the free surface. And then regarding the second part, we have presented one of the first applications of EnVar methods to optimization problems that are not data simulation problems. We have checked that adding Nesterov momentum and variable sigma h improved the performance of the algorithm. And we have successfully applied it to the optimization of interfacial flows. And although I didn't have the time today to present it, we also applied it in the context of nonlinear stability analysis, which can be set up as an optimization problem. And in terms of future work, we would like to extend and verify that the method works properly in 3 dimensions. We would like to move from the level set to volume of fluid or front tracking, so we don't have these problems of conservation of mass for the moving interface cases. Then we would like to avoid some issues related to the pressure projection method by using a coupled pressure velocity solver. And for contact lines, we would like to move from the Navier-Slip boundary condition to the generalized Navier boundary condition, which is better. And for part 2, we would like to analyze the performance of other versions of the EnVar method that are available in the literature. Because actually, when you check the EnVar method, each person that uses a slightly different version, and it will be interesting to analyze how these different versions actually perform in the same context. And finally, I think we will have to apply the EnVar method to a wider range of optimization problems, because right now we don't have many different cases, and if we want to actually verify how good this method works, we need more applications. And with that, I would like to conclude my presentation.